This is Module 11, examples 1, 2, and 3. So we'll start on packet page 204. Example 1, testing if a die is fair. A gambler is accused of using a loaded die, but he pleads innocent. We will check if the die used by the gambler is fair or not. Each throw can be classified into one of 6 categories, depending on the face. Our face choices here are 1, 2, 3, 4, 5, or 6 spots. So in scenarios such as this one, when there are more than 2 categories, statisticians use the Chi-Squared test rather than the z-test. So this is the Greek letter chi, and so we call this the Chi-Squared test. The z-test would be appropriate for a question about the average roll from a die, but not a question comparing 6 categories. Remember, with the z-test, we can compare 1 proportion or 2 proportions, but in this case, we're looking at 6 different categories, so we would have 6 different proportions to compare. So in this case, the Chi-Squared test is the appropriate test. Here's a record of the last 60 throws of the gambler's die, and this is the die that we're checking to see is it loaded or not. Part A asks, if the gambler is innocent, how many times do you expect each number to turn up? Explain your reasoning. So a fair die will have each number come up 1/6 of the time. Since there are 60 throws of the die, n times p is 60 times 1/6 equals 10. So we expect each number to turn up 10 times. So we're going to make a frequency table. So we make a table to compare the observed frequency and the expected frequency for the die. The observed frequency counts the number of times each face came up, and the expected frequency counts how many times each face should come up according to the model for a fair die. So if we look at our frequency table here, all of the expected frequencies are 10 because if this is a fair die, we expect each face value to come up equally. The observed frequencies I got by counting up the number of times each of these faces came up in the list of rolls up above. So we see it looks like 1 and 2 come up fairly less than we would expect. Those numbers are less than 10. 3 and 4 come up much more than 10. In fact, 3 comes up the highest and the furthest away from 10 of any of these values. And then 5 and 6 come up fairly close to 10, not exactly 10. In a regular die that is fair, we don't expect that we're always going to see a perfect 10, 10, 10, 10, 10 distribution, but we expect our distribution to be within a reasonable range of 10. So, question C asks us, judging from our work in part B, is the table fair? If not, which face value comes up too often? There are too many 3 rolls. We know the proportion is 1/6 of any particular 3 coming up, and n equals 60 rolls. So we can calculate the standard deviation. So using our formula back from modules 7 and 8, we calculate the square root of 1/6 times 1 minus 1/6, so this is our 1 minus p part of the formula, and then we divide it by 60 and square root everything. So you can check on your calculator, this comes out to 0.048 standard deviations. So now we can calculate the z-score for this statistic. So here's our p hat, 17 out of 63 rolls, minus our p. So I put 10 out of 60, you could have put 1 out of 6. And then that all gets divided by the standard deviation. So again, I'm using the same z-score formula from modules 7 and 8. And we get here 2.43 standard deviations. So the number of 3 rolls are more than 2 standard deviations from the proportion 1/6. So it does seem like we are outside the 95% confidence interval. And I made a note the number of 4 rolls is also suspicious. We can't draw any conclusions yet. Since there are many lines in the table, since there are 6 different face value choices, there's a high probability that at least one of them will look suspicious even if the die is fair. The Chi-Squared statistic combines all the differences from the 6 lines in the table by measuring how far the frequency of each face value is from 10, the expected value. So here's what our general formula is doing. It's calculating the observed value minus the expected value for each face value, squaring that dividing by the expected value, and then adding them up. So remember, sigma, the Greek symbol, tells us to sum up. And so we're summing up for each of the 6 face values all the different calculations. And that is what gives us the chi-squared statistic, which we denote chi with the squared. And you guys can see there's a square in the formula. That's why the name is called chi-squared. So that's where the square comes in the name. So here's how we calculate our chi-squared statistic. So chi-squared equals 4 minus 10 squared divided by 10 for the number of times the 1 face came up. Remember, the 1 face came up 4 times. The 2 face came up 6 times, so we're going to calculate 6 minus 10, square that, divide by 10. The 3 face came up 17 times, so we're going to calculate 17 minus 10, square that, and then divide by 10. The 4 face came up 16 times, so we calculate 16 minus 10, square that, divide by 10. The 5 face came up 8 times, so we calculate 8 minus 10, square that, divide by 10. And then the 6 face came up 9 times, so we calculate 9 minus 10, square that, divided by 10. The reason we use squaring here is because, remember, this is a way to get rid of the negatives. See how when the expected value is higher than the observed value, the 4 minus 10 would give us a negative 6? Squaring helps take care of that negative so that we're not adding positive and negative numbers when we sum everything up. So this is an example of squaring to get rid of the negative. And so if you check and sum everything up, we get 142 divided by 10, or a chi-squared value of 14.2. So when the observed frequency is far from the expected frequency, the sum is large. So when the observed frequency is close to the expected frequency, the opposite is going to happen, and you're going to have a small sum. So to summarize, large chi-squared values indicate that the observed and expected frequencies are far apart, and small values of chi-squared mean the opposite. The observed values are close to the expected values. So to find out if a chi-squared statistic of 14.2 is reasonable, we need to know the chance of getting a chi-squared statistic of 14.2 or more. So in the same way that we're able to calculate probabilities for z-scores, we're able to do the same kind of calculation for a chi-squared. So you can use a calculator, a computer, or a chi-squared table to find the probability. So for this question, we see that P equals 0.014 or 1.4% chance for a fair die to produce a chi-squared value equal to 14.2. So what can you conclude about whether or not the die is fair? If the die is fair, there's only a 1.4% chance for it to produce a chi-squared statistic as big or bigger than the observed statistic. It does look like the gambler cheated, right? Our p-value is less than 5%, so definitely outside the 95% confidence interval. So it does look like the gambler cheated and used a loaded die. So going on to page 206, we see some graphs showing the shape of the chi-squared curve, which depends on the number of possible values in the model. So the general chi-square graph looks like this. It's got a right tail, and the probabilities are out in the right tail. But again, the shape of the chi-squared curve depends on how many possible values. So our die example had 6 possible values. So our die would have a chi-squared graph corresponding to the blue graph, right? And remember, our probability was 1 out of 6 for the die. And so 1 out of 6 as a decimal is a little bit more than 0.15. So if you see, that's right around where the peak of our chi-square graph is. And then if you had a chi-square graph for 11 values, you'd have a curve that looks like the red curve. And see how that has a peak a little bit lower? Because it's going to have a smaller expected value because you've got 11 choices. So depending on how many values you have, whether 6 or 11 or some other amount, your chi-squared graph is going to change. You'll see in blue, this chi-squared graph that has 6 values has what we call degrees of freedom equal 5. And the red graph, which has 11 values, has degrees of freedom equals 10. So the degrees of freedom are always one less than the number of values in the chi-squared. So in order to calculate the p-value for a chi-squared statistic, we need to know the degrees of freedom. Chi-square models can have more than 2 possible values, so the degrees of freedom will change for each model, depending on the number of possible values. So the degrees of freedom is always the number of values in the chi-squared minus 1. So for the gambler's die example, there are 6 minus 1 equals 5 degrees of freedom. So we're going to check the table, right? We can also get values from our calculator, but we can use a table. So we're going to check the chi-squared table below to verify that chi-squared equals 14.2 for 5 degrees of freedom is between probability p-value 0.05 and 0.01. So we come down to 5 degrees of freedom, and then we come over to find where is a chi-squared value of 14.2. So that would be between probability 0.05 and between probability 0.01. See how 14.2 would be between 11.07 and 15.09. Before calculators, statisticians use tables like this all the time. Since we'll be doing calculations on our TI calculator, we don't need to rely on the table, but the table is here for reference if you want to use it. So example 2 tells us how to use the TI 83 and 84 calculator for hypothesis testing. So make sure you read through this example more slowly. So what we're comparing is days of week and the number of births. So if births are distributed uniformly, we expect that 1/7 of each births are going to occur on each day. And so this is the number of births in New Jersey in 2003. So this is all the births from the state of New Jersey from 2003. So when you type it on your calculator, you first have to figure out what is 1/7 of this total. So if you do 116,823 divided by 7 days, you get the expected value. So when you type the chi-squared into your calculator, you're going to put the observed values in list 1 and the expected values in list 2. If you're using a TI 83 plus or higher, you don't need to go through the steps to calculate observed minus expected squared divided by expected. So we'll jump ahead and look at how you can do it in a TI 83 or TI 84 plus calculator. And if you don't have one, you're welcome to check one out from the Math Lab. So once we enter our values in list 1 and list 2, we're going to go to tests, and then we're going to scroll down to test D, the chi-squared GOF test. GOF stands for goodness of fit test. And then in list 1, we put our observed values. List 2, we put the expected values. And here, because there's 7 days of the week, the degrees of freedom are going to be 6, one less than the 7 days. And then you can go ahead and click calculate, and you should get an output very similar to this. So we've got a huge chi-squared value. Our p-value is so small that it rounded to 0. Remember, if the calculator gives you p equals 0, then it's so small that it has rounded it off to 0. And our degrees of freedom are 6 as we expect. So that means there's a very low probability if the births are distributed equally that we're going to see results like this in New Jersey. So here's how we write up the formal hypothesis test for this example. This is the kind of format that I expect you to see. So the claim is that births are evenly distributed across the 7 days of the week. So we'll let proportion 1 be the proportion of births on Sunday, proportion 2 be the proportion of births on Monday, etc. So P7 will work out to be the proportion of births on Saturday. The null hypothesis is that all the proportions are equal. So you can either write that out symbolically by saying the P sub 0, the null hypothesis, or the null proportion, is going to equal P1 equals P2 equals P3, etc., all the way down to the 7th proportion. Is all going to be 1/7 of what we expect. Or you can say with words, births are evenly distributed across the 7 days of the week. The alternative hypothesis means that at least one of those proportions is not 1/7, right? If 1 is not 1/7, then that's going to screw up the whole distribution and it's no longer going to be evenly distributed. With words, you could say births are not evenly distributed across the 7 days of the week. So we are going to conduct a chi-squared goodness of fit. We'll use the significance level alpha equals 0.05 since another level is not stated. And then we saw the calculations, our p-value was so small it rounded to 0. So we reject the null hypothesis because our p-value was near 0, and 0 is less than that 5% 0.05. So the conclusion we can make, since we've rejected our null hypothesis, is that there is sufficient evidence to warrant rejection of the claim that births are evenly distributed across the 7 days a week. And here's our evidence. The chi-squared value is over 3,000, the degrees of freedom were 6, and the probability is approximately 0. And remember, when you get a big chi-squared value, you still want to check the chart with the degrees of freedom to see the probability, or check the probability given by your calculator. Example 3 is about jurors in Alameda County. So there was a study of grand juries in Alameda County that compared the demographic characteristics of jurors with the general population to see if the jury panels were representative. The results when they compared for age are shown below. So the investigators wanted to know whether these 66 jurors were selected at random from the population of Alameda County. And so make a note that our ages start at 18 because only people age 18 and over are considered for juries. And the county age distribution is known from the public health department data. So here in our first column is the countywide percentage of jurors. So this table has the expected frequencies, right, for jurors. If the jurors are in fact following the county percentages, we expect they'll follow the same distribution. Now there's only 66 jurors, so the numbers aren't going to match these percentages because these are percentages that add up to 100. But when we look at the proportions, right, when we divide the number of people in each category by the total, we expect to see a close percent. So here's the number of jurors that were observed in this study for this particular group of 66 they were studying. And so note that each of these, we would divide them by 66 to find the percent to compare. We don't need to do that calculation because our calculator will do that, right? It'll find the difference in the observed proportion minus the expected proportion for us. So let's state our hypothesis. So I used words here. You could also write, that these proportions are all going to be equal. So the null hypothesis is that the distribution of juror ages is equal to the countywide distribution of ages. And then the alternative hypothesis, meaning that there's some difference, is that the distribution of juror ages is not equal to the countywide distribution of ages. So we're going to collect the data and type it into our calculator, just as was shown in the last example. So if we go into our calculator, we want to go into Stat button and press Enter to edit List 1 and List 2. So in List 1, I put the expected values, and in List 2, I put the observed values. Because we're going to subtract and square it, it should come out just fine either way. Although maybe we better reverse this. So let's go ahead and reverse it and put the 5 over here and the 42 over here. And we'll see if it makes a difference in calculations. So I'm going to put the 9 jurors over here in List 1. The 23% in List 2. We'll put the 19 jurors in List 1. The 16% in List 2. And then we'll put the 33 over here. And the 19 over here. So now I switched it around so that our observed values are in List 1 and our expected values are in List 2. So now we'll go to Stat. We're going to arrow over to Tests. And we're going to scroll all the way down to choice D, the chi-squared goodness of fit. We're going to press Enter. We've got our observed values in List 1, our expected values in list 2. And then our degrees of freedom are 3 because there was, are they 3 or how many categories were there? Let's look back. If we look back, there are 1, 2, 3, 4 categories. So does everybody see 4 minus 1 gives us that 3 for our expected value? And so we'll arrow down to calculate, press enter. And our chi-squared value here is 51.99, so we can round that to 52. And our p-value is 3, but it's not just 3, it's 3e negative 11, so it's a very small p-value. So we see it does make a difference. Make sure that the observed values are in list 1 and the expected values are in list 2. If you do it the other way, you will get slightly different numbers here. So now if we go back to our evidence, we got a chi-squared value of around 52. If we look back, I rounded this up to be 52, and our p-value is 3.002, and that's e negative 11, so it's a very small p-value. So our p equals 3.0002, e negative 11. I think actually the 2 is in the wrong spot. But anyway, it's a very small p-value. Hope we can fix that. There we go. Now our 2 is in the right spot. So we want to state a conclusion. So the p-value is very close to 0. So this tells us there is sufficient evidence to reject the null hypothesis. It does not appear that the distribution of juror ages matches the countywide distribution of ages.